So let's think. So far, what have we done? We have defined what a vector is, seen some uses for it. We have defined some operations on vectors, including scalar multiplication, vector addition, vector subtraction. And now we've introduced these things called position vectors so that we can bring real numbers into it. We can specify exactly what a vector is by giving its two components. So with this in mind, we need to remember when we first did vector addition and scalar multiplication, we did this all geometrically. Well, now we can bring in sort of the algebra of real numbers into it now that we have components, and we can do the same for magnitude for the length of vectors. So let's take a look at v here is 2, -2, this vector. So again, that means that 1, 2. So 2, -2, the point is right here. That's the point, 2, -2. And then the position vector, 2, -2, has tail at the origin and head at the point, 2, -2, is this vector here. So this is 2, -2, this is v. So what is the length, what is the magnitude of v? Now that we have these components in it, 2, -2, how do we figure out the length? Well, that's nothing more than the Pythagorean theorem, because I can always drop perpendiculars to my axes and get a right angle. So in particular, what I can do here is I can drop a perpendicular to the x-axis. I know that the length of that, even though it's down 2, I'm just talking about the length here, there's 2, that's the length, and I go over 2. So that is the length of v, which we use bars for. So this is the length of a vector. I put vertical bars around it. This is the magnitude or length of v is specified with these vertical bars. Well, it's the hypotenuse. It's the length of the hypotenuse of this triangle that I've drawn. This is the geometry coming in again. And so, using the Pythagorean theorem, it's 2 squared plus 2 squared. Take the square root of that. So that is the square root of 8, or 2 square root of 2, if you prefer. So that is the length of v. All right. In general, let's say I have. Sorry, give me one second. Yeah, let's skip the generality for a second. I'll do that on the next slide. Well, let's do something a little bit more difficult. Let's say I have 2 points in the plane, P and Q, and I actually have quantities for these. So here's -1 is right there, let's say, and 3 is up here. So P, -1, 3, that's here. So there's my point P, and Q is 1, 2, so here's Q. I can form the vector from P to Q, is this one, so that's PQ. Well, how do I find its length? Well, what I can do is I can first make it a position vector. Remember how we did that? That's from earlier, from the last video. PQ, so take the difference in the x components, take the difference in the y components. This goes over 2 and down 1, so PQ. So first off, I can write it as a position vector in terms of its components. It would be 2, -1, right? 2 minus 3 is -1. 1 minus -1 is 2. That's 2, -1. And then I can use this technique here. And so the magnitude, the length of PQ, again, it's just a triangle. It's just a right triangle, so we use Pythagorean theorem. Down 1 over 2, so that's the square root of 2 squared plus 1 squared. So that's square root of 5. This is how we compute length. It's just Pythagorean theorem when we're dealing with the plane here. When we jump up to 3 dimensions, we're going to have to do 2 applications of the Pythagorean theorem. But as we'll see, the formula is very similar. It's very nice. And that's good. So let's see here. In general, how do we compute this? I don't want to have to think too hard every time. So let's just kind of sum this up. If I'm given the points P and Q, the magnitude or length of PQ is x2 minus x1. So this, again, this is taking the position vector. So PQ is this. x2 minus x1, y2 minus y1. That's my position vector for PQ. And then the magnitude of PQ is the distance between P and Q, right? That's how we define magnitude, is the length of that vector. So it's the difference between those two. So it's the difference of x2 and x1, square that, y2 minus y1, square that, take the square root. That's exactly what's going on here. Notice we did have some negatives here, 2, -2, that if I would have written this as -2 squared, I get exactly the same result because we're squaring it. And that's going to get rid of the negative. So here, this was -1, the same as that. So this is all we're doing, is we're squaring each of the components and then taking the square root of that. And that's coming exactly from the geometry of the situation, that what we're really doing is we're computing the length of the hypotenuse. That is, we're computing the distance. This is an important thing, the distance between P and Q. And so what we have here is the distance formula. This should look familiar to you. This is the same as the distance formula between 2 points. If I have a position vector already, and I'm not just computing between two, well, then we get to skip a step. We don't have to do this x2 minus x1, y2 minus y1 business. Instead, if we have a position vector, we can just square each of the components and take a square root of that. That's what we did with this first one. So that's how we can compute magnitudes exactly now that we have components position vectors. We can also do vector addition like this. So let's say I have two vectors, u1, u2, and v1, v2. So I'm just going to draw these somewhere in the plane. So maybe u is something like this. And that goes, remember, that's going to go over u1 and up u2. And let's do, how about v is, let's do something like this for v. This is going up, or this is going up v2. v2 here is negative, and over v1. v1 is positive here. And let's figure out, so what we want to do is we want to figure out how do I write the addition of these two vectors. So this is not a definition here. We defined vector addition geometrically, and so we're going to do it geometrically. So I'm going to take u, and maybe I'll plop it down here. How about, it doesn't really matter. And I'm going to take v, and I'm going to use the triangle rule here. So this is u, sorry, this is v, this is v again. And I'm going to use the triangle rule. So the vector u plus v would be this one. And what are its components? Well, let's see. By putting the tail of v at the head of u, the x component of u plus v is going to be the sum of the two x components of u and v. Right? This is length u1 here. This is length v1 here. So that's the x component of u plus v is just u1 plus v1. Wow, doesn't that work out nicely from the geometry? And same for the y component. I go up v1, and then I go up v2. In this case, v2 is negative, and so it almost nearly cancels out u2. And what I end up with is the sum of u2 and v2 for the y component. So that's pretty cool that it works out like this. Again, this is not a definition. This just comes from the geometry that the sum of two vectors should be the vector whose components are the sum of the components of u and v. Works out very, very nicely. That's how we know that we sort of have the right definition for addition, is that it works out like this. And then difference, again, similarly, we can first take negative v. That's going to make it minus v1 and minus, right? Minus v would have position vectors minus v1, minus v2. And then when I add them based on what we just talked about, sorry, that looks like a minus v would be this. And so when I add them together, I have u1 minus v1, u2 minus v2. So again, works out nicely. The difference, the components of the difference of two vectors are the difference of the respective components. Works out very nicely. I also want to point something else out here with vector subtraction. Is again, if I take another geometric way to think about vector subtraction. Let me grab u again. I'm going to grab v. And I'll do it like I'm adding them. And instead of doing u plus v here, I'm going to demonstrate u minus v. One way we can get u minus v is to actually go the other direction as u plus v, like this. So there's a triangle rule for these. Wait, turn 1 second. Yeah, this would also, sorry, no, that's negative u plus v. That's not quite it. That's not quite what we want here. Let me try and get this. That's not quite what I'm looking for. Again, let me take u. I know what I'm going to do. Instead of doing that, I'm going to take u and v. Boy, let me move these. Sorry, everybody, bear with me for a second. So there's u and v. Another way I can get u minus v. So think about minus v is going to come up like this. Minus v. And I can put that over here. So this would be minus v. And then across like that. So this would be u plus minus v. This vector would be u minus v. Just geometrically, that's what it would look like. Another way I can get that u minus v is to take u and v and put them like I have here with tails together, and then go from the head of v to the head of u. Again, this gives me u minus v. And we can see that with the parallelogram that we have here, that this is going to be u minus v as well. So that's another geometric way to think about vector addition. I can take the two, put their tails together, and draw it like this. And that's another way to see that u minus v should be u1 minus v1, u2 minus v2. All right, so that's vector addition in terms of their components. We also have scalar multiplication in terms of components. So let's say I take a vector like, I'm going to actually give this some components. I'm going to do 1, 2. There's the point 1, 2. Here's the vector 1, 2. So I can scale this. I can multiply it by a scalar. I can scale this thing. Let's say I scale it by 2. So I take 1, 2, and I increase its length by 2. So what happens to the components when I increase the length of u by 2? Well, I double its x component, and I double its y component. So this would be at 2, and this would be at 4. Does that make sense why I would double the x component and double the y component to get this vector? Hopefully. And what I get here is, so this would now be the point 2, 4. And so 2u is the vector 2, 4, which, as you'll notice, is 2 times 1 and 2 times 2. I'm doubling each of the components. So what's going on here is this. Down here, when I scale a vector, so c, a real number, times a vector v, so 2u, something like that, or I can write this. I could also write this as 2 times the vector 1, 2. And what we're essentially doing here is distributing the scalar to each of the components. Again, this is a way to tell us that our scalar multiplication, our geometric interpretation of this, is lining up with our algebraic or analytic or numeric notion of this, because of this nice property where we're essentially distributing the scalar through to each component. It works out that way. Same thing if I multiply by a negative. So what would negative u be? Well, I would just go in the exact opposite direction. Same length, but opposite direction. So what that would mean is that I would go, instead of going up 2 and to the right by 1, I would go down 2 and to the left by 1. And so negative u, or negative 1, 2, again, it's the same with negatives. What we're doing is basically distributing that negative through to each component. So that's the geometric definition of scalar multiplication. If we want to be more exact and numerical about this, now we have a way to do that. C, the scalar, just comes through to each of the components. The magnitude of the scaled version of C, or of U, so the magnitude of CU, is the length of this, and what this is going to be the absolute value of C times the length of U. So why does this work out the way it does? Well, let's actually do that. Let's work that out. Why is this true? That the length of CU is the absolute value of C times the length of U. We can actually completely work this out now. This might be a little bit more fun for the mathematics students in the class, but this is important. We're going to be doing quite a bit of this in the class, actually understanding why these things are working out, proving things, proving theorems, stuff like this. So let's see. So C is some real number, and I have U, so U is U1, U2. So let's see. CU, we have here is CU1, CU2. Those are its components. And so let's see, what's the magnitude of CU? Well, I'm going to use that magnitude formula. It's going to be C times U1 squared plus C times U2 squared. All right, let's work that out. Well, I have a product here being squared, and so I can write this as, each of these, I can write this as C squared times U1 squared plus C squared times U2 squared. Now I have two C squared times U1 squared, C squared times U2. I can bring that C squared out. So this is now square root of, I'm going to write it as C squared times U1 squared plus U2 squared. And that's looking pretty good. Let's keep going with this. I now have a square root of a product. I can separate this. This is square root of C squared times square root of U1 squared plus U2 squared. Square root of C squared is not just C, right? For example, if C is negative 2, C could be negative. C is negative 2. I square negative 2, I get 4. I take the square root of that, I get 2, not negative 2. So the square root of something squared, these aren't inverses of each other. They're half inverses. They're one-sided inverses of each other in terms of functions. What I get is not C, but rather the absolute value of C. And then right here, so this guy right here is absolute value of C. And then this guy right here, well, that's square root of U1 squared plus U2 squared. That's the magnitude of U. So what we get here is magnitude of C times magnitude of U. And that's exactly this result here. So scaling a vector scales the magnitude by the absolute value of the scalar. Pretty cool that we can prove that. Again, some may think it's less cool than others. I think it's pretty cool to actually prove that outright with all of this stuff that we, just from these first principles. Okay, at any rate, that's the end of this video. I'll see you next time.